All right, so this is going to be section 9.3 where we're going to be talking about determinants. And then after we look at determinants, we'll show you how to use determinants by solving using Cramer's rule. All right, so first of all, finding a determinant of a 2 by 2. We're going to be looking at 2 by 2 matrices and 3 by 3 matrices. We won't look at any other sizes. Those are the only two that we'll be looking at. So in order to find a determinant of a 2 by 2, we'll do this by hand. What we'll do is we will multiply on the diagonal, so that's what you see right here, and then we will multiply on the other diagonal, and then we're going to subtract those two terms. For the 3 by 3 matrix, you'll notice that we're going to be using the calculator, and in a moment you should pause your calculator, or sorry, pause the video and get out your calculator and see if you can do a 3 by 3 matrix in just a few moments here. And get the determinant of it in the calculator by following these instructions. But first, how do we know the difference between a matrix and a determinant? Matrices, notice that they have brackets. They've got these square brackets. And a matrix is an array of numbers. A determinant, on the other hand, is not shown by square brackets. It's got these vertical bars. And a determinant is actually going to be just a single number. It's not an array of numbers. It's a single number. All right, so to get that 3 by 3 matrix, go ahead and pause the video and try on your own to get example number 3, its determinant, and see if you can do that. All right, now that we're back, let's go ahead and find the determinant of a 2 by 2 matrix. We'll do this one by hand. So remember, we will multiply on the diagonal, and then we will subtract those two. So here is the two sets of multiplying, which is going to be negative 20 plus 16, and that will be negative 4. Now, if we're going to use the calculator, I've already placed this particular 3 by 3 matrix into my calculator. And so if you follow the directions, you already know what to do. But we're going to go into our matrix menu. We'll go into the math column, and number 1 in the math column is our determinant. And then we need to tell it what matrix we're going to use. I personally saved mine as G. And so when I put that into my calculator, I'm going to get 60 for my determinant. All right, so then how do we use a determinant? Determinant is used in Cramer's rule. And so we're going to do 2 examples of these. One of these is going to be a 2 equation system. And then in a minute, we're going to do one that is a 3 equation system. All right, so in order to find Cramer's rule, you remember we have solved by elimination, we have solved by substitution, we have solved by reduced row echelon form. So there's several different ways that we have solved so far. Cramer's rule is just another way of solving a system of equations, and you can see here is our normal system of equations. So what we're going to do is the first thing we're going to find is what I call the plain old determinant. The plain old determinant is where I use the coefficients from the x's and the y's, and I get a 2 by 2 matrix, and I find its determinant. And then I'm going to find d sub x, and d sub x is going to be found by taking the constant matrix, replacing the x's with the constants, leave the y's alone. And then d sub y is where we'll take those constants, replace the y's with the constants, but leave the old x's alone, leave the x coefficients alone. Find all 3 determinants. Once you have found all 3 determinants, to get your x and your y value, you're going to get the d sub x divided by the plain old determinant, or you're going to get d sub y divided by the plain old determinant. All right, so one little note here, if your determinant is equal to 0, then Cramer's rule cannot apply, and the reason for that is you cannot have a 0 in the denominator. All right, so we're going to find our determinants by hand since there are only 2 by 2s here, and I've already set these up for you. So you'll notice that my first determinant is just simply my x and my y coefficients, and so my determinant is going to be negative 11. Notice that to get d sub x, I've taken my constants and I replaced the x's with the constants. I left the y's alone, and I got my determinant sub x as negative 19. And then for d sub y, we'll take our constants and replace the y's with our constants, leave the x's alone. And so we'll have 18 for d sub y. Well, now we can use the rule. We can use Cramer's rule. And we can say to get our x value, we're going to do d sub x divided by d. And so that's going to be negative 19 divided by 11. To get our y value, we'll do d sub y divided by d. And that's going to give us an 18 over negative 11. The only cleanup to do is those negatives on the x values. And so the x value will be positive. So we have 19 elevenths and negative 18 elevenths. You could check your work by going back to the calculator and trying reduce row echelon form. You could also use substitution or elimination to check your work on these. Now, the general rule for Cramer's rule is that I can adapt this to any number of equations in my system. And basically what happens is we're going to have, to get the x value, it'll be d sub x over d. To get the y value, d sub y over d. To get the z value, d sub z over d. And so on and so forth. We will never get past three equations in this particular course, but this does expand to any number of equations. So that's what that gray box says. So to apply Cramer's rule for a 3x3 system, notice that the first thing that I did was I took my column of constants and took them all over to the right side. And so that way they're written properly, where I only have coefficients of my variables on the left side of the equal sign. My constants are on the right side of the equal sign. And so in order to get my plain old determinant, I'm going to use the coefficients of my x's, my y's, and my z's. Now, I already have this saved in my calculator, so just to save some time, you might want to pause the video at this point, but in order to save some time, I went ahead and answered it in already. So I'm going to find my determinant, and I'm going to use the matrix that I called B, and so this is going to equal 60. To get my d sub x, notice that I have taken my column of constants and I've replaced the x's with that column of constants. And so I named my matrix C here. So we'll go back into our matrix menu, go to the math column, pull out determinant. Uh-oh. Let's try that again. And I will use my C matrix. And so for this one, we have 90. And to get d sub y, I have my constants replacing the y column. So go back into the calculator, go back to the matrix menu, get the determinants, and I named mine matrix D. So it's going to be negative 150. And then lastly, do the same thing for d sub z, and you should get 360. So now you have 4 different determinants. And so our solution, you'll see, is going to be a 3-part solution. And so we'll just take each of the things that we found. So d sub x over d will be 90 over 60. And yes, I will reduce my fraction. For the y piece, negative 150 over 60, and for the z piece, 360 over 60. So then to reduce each of my fractions, that'll be 3 halves, negative 5 halves, and 6. All right, so then one more thing here, show that Cramer's rule does not apply. Remember that up here we said if d is equal to 0, Cramer's rule does not apply. So all we would need to do with this is just simply show that our determinant is equal to 0, our plain old d. So this is going to be my coefficient matrix, where I'm only using the coefficients of x, y, and z. And so if I go ahead and pull up my calculator and get the determinant of f, notice that this particular determinant is equal to 0. So we can say that because that would cause a 0 in the denominator for each of the 3 pieces of my solution, this is not a valid way to find a solution. Again, when my determinant is equal to 0, the system is either going to be inconsistent or it's going to have infinitely many solutions. We just don't know which. We would need to solve it in another way.